Hi guys, Assalamu alaikum. This is Arif. In this video, we are going to see how we can design a program counter using the structural model approach. First, using SystemVerilog program and then using a VHDL program. So this is a SystemVerilog program design file first, in which we have defined a module which is PC, and it has two outputs, PC and next PC, which are of 8 bits. And then we have defined some inputs which are power clock, branch enable and stop enable. These are 1 bit. And then there is another input which is going to give us the branch address, which is an 8-bit input. And after that we are defining this PC as rec, and these lines we right now don't need. And then after this we have defined an always block, and in this we are assigning next PC to PC, and this is actually a 8-bit D flip-flop or a register, and this is the main component of a program counter. A program counter is just a special case of a register. And after that we are going to define some combinational logic inside this program counter, and for that we are defining this next PC as reg. And then in the second always block we are going to see the inputs power, stop enable, branch enable and PC, and then we are going to apply some if else conditions. And first of all we are going to say if power is going to be 1, do some functions, and if power is going to be 0, make next PC equal to all 0 bits. So this is the way we can initialize our next PC. And once power is going to be 1, then we are going to check our stop enable signal. If it is going to be 1, we are going to make the next PC equal to PC. We are no longer going to increase our PC. But if there is no stop enable, then in this else block we are going to check branch enable signal, and we are going to say if branch enable is going to be 1, make next PC equal to the branch PC address. And otherwise we are going to say if branch enable is going to be 0, that means that increase this PC by 1 and then place it inside next PC. This is going to be our next PC address. And this is first of all a behavioral design, and we are going to now convert this behavioral design into a structural design in this video. And look here, we are inside this sequential logic, we are using this non-blocking assignment, and inside these combinational logics we are using this blocking assignment here. So this is our complete program. Now let me show you the test bench as well, which we are going to use to simulate this. And this is our test bench module named test bench, and inside this we are defining our outputs as wire and inputs as rec. And then we are calling here our main module, and we are using these wires and regs. We are going to map our inputs and outputs accordingly. And after that, in this initial block we are defining our clock logic here like this, so that we can run our program counter according to a clock. And in the second initial block we are saying that give our inputs these values 000, and branch PC is going to be this. And same way we can apply different signals to our inputs, like here we are making this equal to 0, this equal to 0 and power equal to 1, and we are giving branch PC the address like this. So this is the way we can apply different combinations. Then we have end module, and now let's simulate this program so that first we can understand its behavior. Go to test bench, simulate, Now let's run this simulation and we are going to see this output. I mean, these are the combinations of our inputs to the outputs, and here we are updating our PCs and next PCs. This is our branch PC. Here we are applying the branch enable, and that's where we are getting this value branch PC inside this PC and next PC. So this is the way it is going to work. Close this simulation, and now we have understood our behavioral logic of our program counter, the way it functions. And now actually I am going to implement this program in just another way so that we can use this design for our structural model. So comment this, and we are going to comment out these lines. And now this is the same logic but using the assign statements, which are continuous statements. And here we are making this increment PC equal to PC plus 1. We have to just declare some new variables which are going to be wires. So these three wires we are defining here, 8 bits, temporary PC0, temporary PC1, and increment PC. And these we are going to use here. We are making this PC plus 1 in our code. This one to increment PC, same way we are applying this logic. If branch enable is going to be 1 or 0, this thing we are going to store inside this, and after that this thing stop enable we are going to store inside here temporary PC1, and this is actually the same logic. It is very easy to understand. So let's compile and run this program. So the procedural assignments and the concurrent assignments behave a bit differently in SystemVerilog. So we are going to see a little difference in the way the waveforms we are going to see. So these are the same outputs and inputs, but I mean, instead of going to the next clock cycle and updating these PC and next PC values, it is going to update in the same clock cycle. Once it is going to see here branch PC, and it is going to enable this branch enable signal. So this is just the difference, but the logic is going to be same, and the results. So we can come here, and now these are those code lines which we can use to implement our structural design. So this we can make another module for this logic. Same way we can make another module which is going to be a 2 to 1 mux for these three lines. Next three lines. This is going to be our increment circuit. Separate module, and this one. Same way if we are going to go upwards, we are going to see this one. This is just a D flip-flop 8-bit. So we can implement these code lines using a separate module as well in order to implement our design as a structural model. So comment out these lines, and Now we can first of all define three new modules. So we need a D flip-flop, a 2 to 1 mux, and a increment circuit. And those three we can get from these code lines. So this is a module we have defined D flip-flop. This is the second module, increment circuit. This is going to be our logic inside this, and third one is going to be this mux 2 to 1 8-bit mux, and select line input 1 and input 0. This is the way we are going to design this. Now using these three modules, instead of implementing those above four lines, we can use these code lines. So this is going to be our increment module. We are calling here this inc 8. These are those mux 2 to 1 8-bit mux, and these are the same signals which we are applying here, which are in above four lines. Also, we have to make a change here as well. We can skip these code lines and implement these as circuit as well using this module DFF, which we have defined above. So this is that DFF we are using here, these two signals here. Same logic we are going to use, and we can implement this as a structural model. Now save this design, compile this modified code, come here, simulate, run simulation, and we are going to see the same outputs and input combinations the way we saw earlier. So this is the way we can convert our behavioral design into a structural model using SystemVerilog. And now I am going to flip over to VHDL project and show you how we can implement the same thing inside a VHDL code. So open this project. So we are inside the VHDL project, and now I am going to first of all show you our design file. So this is our program counter, this entity PC. It has same inputs and outputs, and here we are using this in out to define our PC and next PC as in out as well. Reason I can tell you later why we are not using here out. And after that, in this architecture of PC, we are saying here begin, and inside process log we are going to say this is our register. So on this clock, assign this next PC to PC. So this is our that register for a D flip flop, the key component, and then here is our combinational logic inside this second process block, and we are going to check our four inputs: power, stop enable, branch enable, and PC. And after that, we are going to check first of all if the power is going to be 1, then we are going to check stop enable is going to be 1, and if it is going to be 1, we are going to say don't increase PC, so just assign PC to next PC. So this is going to be our next PC, same at the same point or PC address we are going to stop. And due to this reason, because we have to use here our output PC as an input to next PC as well, that's where we are going to define here PC as in out here, not PC as out. And same way we have to define next PC as in out as well. Although in this program we are not going to use next PC as input to something, the way you can see it here, we are just assigning the values to our next PC. But for some larger design code where we have to use this PC module to a CPU design or anything like that, there we would be able to see that we have to define this next PC as in out as well, because we can use then this next PC in our larger design as an input as well, because we have to assign its values to some other signal as well. Just like here we are assigning this PC to next PC. So in a larger circuit, we can assign next PC's value to that circuit as well. That's why we are defining here next PC as well. But in this code, if we are not going to define this PC as in out, just as out, we are going to see an error. So after that, we are going to check this branch enable signal, and we are going to say if branch enable is there, that means we have to take our PC to that branch address. Otherwise, we have to just increment our PC, and that is going to be our next PC. And here we are saying if power is going to be 0, initialize this next PC as 00, all bits zeros. So end of the process statement and end of our architecture. Same logic, and now we can see our test bench code as well. So here we are defining here test bench entity. After that, its architecture. Here we are using this PC as a component, because this is what we are going to simulate using this test bench. And after defining these signals for the mapping of inputs and outputs, we are going to call this same entity PC here, and we are going to map those inputs and outputs using the positioning using this port map. And after that, we are going to define this process block, and this is going to give us our clock logic. And in this second process block, we are going to keep the values to our input signals, like power is going to be 0, stop enable 0, branch enable 0. Then we can change these 1 0 0 0 1 0. We can try all the combinations to these inputs. These are the four inputs, and this is going to be our end process, and then our architecture is going to finish here. So let's compile these designs, and now let's simulate these designs. Run the simulation, and we are going to see these input and output combinations. Here we can also see, here we have our branch enable, and after that we have this branch PC, and next PC is going to be this one, but at the next clock cycle we are going to see PC updated to this branch PC, and this is the way VHDL design is going to behave in simulation. So now let's go to this design file and see how we can implement this behavioral logic using a structural design. Let's comment out these lines. And now we can include these lines. So same logic we have applied here as well, like we did in those if else statements. So we are saying here we have to define actually three more signals. So these we can define here. Those are vectors 8 bits, and the increment PC, temporary PC 0, temporary PC 1. These we are going to use here, and we are going to say increment PC is going to be PC plus 1, temporary PC 0 is going to implement this, check this branch enable and give the signals like this, and same way this line is going to check the stop enable signal, and this is going to check our power signal the way we were doing this, like here branch enable logic, here stop enable, and finally this power. So same logic. So these are those code lines which we can use to implement our design as a structural model. So this is just a increment circuit. These three lines are just our 2 to 1 muxes, and this is just a 8-bit T flip-flop. So what we are going to do is we are going to define three more entities. So we can comment out these lines. So this is our first entity T flip-flop. This is its logic, this architecture, and this is its logic inside this architecture, clock, and this one. Same way this one, mux 2 to 1. This is going to be its logic inside this architecture, and now this increment circuit we have to choose as well. So we can comment out these lines as well. So this is going to increment like this, input increment by 1 and place inside output. Now these three entities we can use as components in our design. So uncomment these lines. So these are those components, DFF, increment, and mux 2 to 1. And now actually using that DFF design, we can implement this code line. This is just a 8-bit T flip-flop. Implement these lines and use that T flip-flop here. This is the way we can map the inputs and outputs. Go downwards. Instead of using these four lines, we can implement these as a structural model as well. So we have included these lines. This is our increment, this our increment circuit entity. This is the way we can use the port map here, and then our first mux, we are going to use that mux 2 to 1 first of all at this line to implement our this line, second line, and then this line we are going to use to implement our this third line, and this fourth line we are going to use to get our final next PC value. So go here, save this, compile this, and simulate. Run simulation, and we are going to see the same input and output combinations here. So this is the way actually guys we can implement a program counter using a structural model in VHDL. We have to just design using the behavioral model approach, and then using that behavioral model approach we can convert our circuits into a structural model. So thank you guys. I hope you guys have enjoyed this video. Have fun.